Hi everyone, we're going to discuss in this video some basic ideas about chemical bonds and how atoms are connected together using these concepts that we call chemical bonds. So bonding theories are really important in chemistry because most of the things we see around us are molecules or compounds, which are things that are made up of combination of atoms. And so understanding how these atoms combine together to make these larger compounds is going to be critical to understanding how chemical reactions work. Now, it turns out that not only does bonding theories help explain the physical and chemical properties, it also can help us understand the shape of a molecule, what it looks like in three dimensions. One important example of how shape explains a molecule's property is the structure of the DNA. Once people understood that has a double helical structure, it immediately helped the scientists understand how DNA could be used as a way to transmit genetic information. Now there's two different bonds that we're going to discuss in this video. We'll give a brief overview of ionic bonds and covalent bonds. Ionic bonds is a bond that's formed when a cation and an anion combine to form an ionic compound. And a covalent bond, on the other hand, is when two non-metal atoms combine to share their electrons. The way we're going to illustrate these bonds is to use something called a Lewis dot structure or electron dot structure. This is just a technique or a tool that we use in chemistry where we represent the valence electrons using dots. So let's talk about how that works. These Lewis structures is set up the following way. First, you have to figure out the number of valence electrons that you have for that specific element. Remember that valence electrons are the outermost electrons in an atom, and those are the electrons that we would either share or lose, and the valence shell is where we might gain electrons whenever there's a chemical reaction. So we don't care about other electrons, we just care about the valence electrons. In oxygen, for example, the electron configuration is 1s2, 2s2, and 2p4. The valence electrons are all the electrons that are located in the valence shell. In this case, the valence shell is the largest shell that we have, which is shell number 2. So we have 6 valence electrons here. The easy way to remember how to count valence electrons is just to look at the element group number. Oxygen is group 6A, so it's going to have 6 valence electrons. And the way you draw that is you put the 6 dots around the symbol for oxygen. So lithium has 1 valence electron, so it's just written this way. Fluorine has 7 valence electrons, so it's going to be drawn this way. As we learned in the previous chapter when we talked about electron configuration, noble gases are extremely stable because their s and p orbitals of a given period is completely full. And so we find that the number that corresponds to a full orbital for the s and the p are 8 electrons because there's one s orbital and there's 3 p orbitals. And so this gives rise to a rule that's called the Octet Rule, where octet means 8, which just says that if an element can form 8 electrons around itself, then it becomes stable. So Lewis, the person who invented this way of drawing, proposed the idea that in order for a compound to be stable, it must satisfy the octet rule, meaning that the element must have 8 electrons around it. So our goal, as you'll see when we draw Lewis structure, a lot of times is to represent the 8 electrons around a particular element. Now that we understand how to draw simple Lewis structures for elements, we can progress to drawing structures for ionic compounds. Remember that in discussion of periodic trends, we noticed the following, that metallic elements, which are elements on the left side of the periodic table, tend to have low ionization energy. And that, of course, means that they can lose their electrons fairly easily to form cations. So we know that metals tend to form cations. Non-metal elements on the right side of the periodic table, they tend to have high electron affinity, which means that they can accept electrons very easily, and therefore non-metal elements tend to form anions. Now, when the cation and the anions come together, electrostatics tells us that opposites attract, so the cations and the anions would want to form attractive interaction, and that attraction is what we refer to as the ionic bond. So an ionic bond is nothing more than an electrostatic attraction between a cation, a positively charged species, with an anion, which is a negatively charged species. Now in the Lewis model, the way we represent a cation and anion is by drawing the two elements together. So for example, potassium chloride, the ionic compound. In this case, we start with potassium and chlorine separately. Potassium is a group 1 element, so it has 1 valence electron, and then chlorine is a group 7 element, so it has 7 valence electrons. When potassium and chlorine bond together, they have to satisfy the octet rule, which means that they have to have the electron configuration of a noble gas. The easiest way to do this is for potassium to lose that 1 electron and for chlorine to gain that 1 electron. So it'll become something like this, where the potassium becomes potassium ion, the chlorine becomes the chloride ion. When something has an ionic charge on it, we draw in the Lewis structure, we would draw it as the element with the electrons around it, put a bracket around, and then on the outside put the ionic charge. So in this case, that's what it looks like. K in this case doesn't have any brackets around it because there's no electrons around K. So it's just K plus. The Lewis model allows you to make prediction about what kind of formulas you can get when you combine a specific metal with a specific nonmetal. So for example, if you have sodium and sulfur, we see that sodium has 1 electron on the valence shell and sulfur has 6 valence electrons. So to make that combination of an ionic compound, each sodium can lose 1 electron, but the sulfur is going to need 2 to make that octet or 8 electrons around it. So that means that you're going to need 2 sodium to make a stable compound between sodium and sulfur. So as a result, we end up having this particular structure right here where each sodium loses 1 electron. So you got 2 sodium ions, Na plus on each side, and then the sulfide ion, which is formed by the sulfur gaining 1 electron from each sodium, then has this structure with the brackets around and with a 2- charge on the outside. We're now going to talk about how to draw Lewis structures for covalent compounds. With covalent compounds, what you have is 2 nonmetal elements sharing the valence electrons. That leads to 3 different types of bonds that you may have in covalent compounds. The first one is something we call a single bond, when the 2 elements share 1 pair of electrons. So the example that's given here is in the water molecule. The hydrogen brings in 1 electron, the oxygen brings in another electron. That becomes 1 pair, and that 1 pair is 1 bond, which we call a single bond. So in water, whose structure is shown right here, there are 2 single bonds. There's 1 single bond right here between H and O on the left side, and then there's another one on the H and O on the right side. So instead of drawing 2 dots, we draw it as a line. And so this is 1 pair of electron, and this is what we call a bonding pair, because it's the pair of electrons that's bonding the 2 elements together. We also have this pair of the electrons on top of the oxygen, which is not used for bonding. That's just oxygen's own pair of electron. So that one is called a lone pair or non-bonding electron pair. So in a Lewis structure for covalent compounds, you have 2 types of pairs of electrons. You have the bonding pairs, and then you have the non-bonding or lone pairs. In certain cases, you might need 2 bonds, so we call that a double bond. An example here is with the structure of oxygen, 2 oxygen atoms next to each other. The only way where both oxygen atoms can have the octet configuration, which is the configuration of a noble gas, they have to share the electrons so that they share 2 pairs between them, which is shown in this structure right here. And so those 2 pairs can then be represented as 2 lines, and so that's called a double bond. You may also need to form a triple bond. This is illustrated by the structure of the nitrogen gas, or N2. In this case, for the 2 nitrogens to have octet, you have to share 3 pairs of electrons around the 2 nitrogens, and that makes 3 lines or a triple bond. One more thing to note is that because the more bonds you have, the more the nuclei are pulled closer together. The triple bonds are the shortest bonds we have, but also the strongest one.